Good. So now we work with this definition of universal hashing, and I guess next we're going to see, I guess, a generalization of this. And sometimes this is not enough, and this is kind of one natural strengthening of this definition. So now we're going to say, sometimes called strongly universal. Sometimes it's called pairwise independent. Both the names were the same. So what is the requirement here? So the requirement here is that for all x not equal to y, again in this universe that we're hashing, it should be the case. Oh, let me add one more constraint here. For all u comma r in the output range, not necessarily different. It should be the case that the probability for the random choice of the hash function that hash of x is equal to q and hash of y is equal to r is exactly what a truly random hash function 1 over m squared. This is the definition of strong universality or pairwise independence. There's also an approximate version. You can look it up in the reading material. Let's just ignore it for now, but it's just some slight relaxation of this. This is a little bit stronger than before, because it's also why it's called strong universal. Maybe let's see that if I have a strongly universal hash function, I also have a universal hash function. Right? Maybe that's just a quick sanity check for the name strong universal, because if I want to have a universal hash function, I have to check that the collision probability is small. So how could I check that? I can see, well, what is the probability that hash of x is equal to hash of y? Well, it's the sum over all possible q's. The probability that they both hash to that. Hash of x equals q equals hash of y. If I am strongly universal, this number is 1 over m squared. By definition, there are m terms, and then I get 1 over m, which is what I need for universality. If I have a strongly universal hash function, I also have a universal. The other reason why you look at this name, pairwise independence, is basically because since these probabilities are exactly 1 m squared, to show that the hash of x is uniform random, the hash of y is uniform random, and they are independent. If you look at the pair of the hash of x and the hash of y, then they are independent of one another. So that's why it's pairwise independence. If I look at any two hash values, then they're independent. This is not the same as saying that hash of x is independent of all the hash values of the rest of the universe. That's not the same. I guess we'll see why. Actually, here we will not prove that any of the concrete hash function is strong universal. I think I'll just show you two examples, and one of them basically we have almost given the proof. So maybe let's just look at two examples here. So one of them is multiply mod prime. Almost the one we saw. So at least in the simple case where m is equal to p. So you're not reducing to a smaller universe, you're just hashing them to numbers in the same range. This will actually make sense for some applications we're going to see. If you're actually outputting just to a range that is as large as this p, then if you just pick a and b independently, uniformly at random, this time we're not picking a non-zero, we're just picking it randomly from 0 to p minus 1, we're picking b randomly from 0 to p minus 1, then we can show that this is actually a strong universal. And we basically gave the proof. If you remember, what we showed was that if I fix a pair x and y, fix a pair of distinct keys x and y, then we introduce these q and r pairs, right? The hash value of x, when we did the mod p but not the mod m of that p. We also had the other hash value, was basically the hash value of y before we did the mod m, and we only did the mod p, right? And then we argued there was this one bijection between the choice of a, b, and these values q and r. Hope you remember that argument. Right? Which means if we're choosing a and b uniformly at random, the two hash values Q and R are also going to be uniform random. And so then they satisfy this difference. Because they're uniform random amongst all the pairs. And if M is equal to P, and that's the assumption, if M is equal to P, then we actually get this 1 over P squared chance that we see a complete pair. It's uniform on all the P squared pairs. For this one, you can easily modify the proof, give that guarantee. If you want to include the mod M, you have to introduce this approximate version because it causes small troubles, but it almost satisfies this guarantee. But we will not go into that. I think it's just technicalities. But again, we also saw that this one is not so practical to implement, right? There's annoyances. So there's actually also a version of this, the other one, the multiply shift, that works here. So there's a slightly different version of multiply shift. But here we're again hashing from, so here our hash function will be from 2 to the W to 2 to the L, if you remember. Here, let's introduce another number, W bar, in which if we're going to require that W bar is at least W plus L minus 1. What do we do now? Now we pick A and B uniformly at random and independently in 2 to this W bar, slightly larger bits. And then our hash function is basically the same as before, but it's this A times X plus B now. And then we're going to do modulo W bar. And then we're going to take this number and do integer division by 2 to the bar minus L and round. So this is exactly the same hash function as we saw before. Only difference, we're adding a B now, and then we're requiring that this number of bits where we're choosing our hash values in is somewhat bigger. Before it just had to be at least W. Now it's a little bit bigger. It has to be at least W plus the number of bits we're hashing to minus 1. So maybe an example is if you know your input numbers are maybe only 32-bit numbers, and you're hashing to 20-bit numbers, then you can pick W bar to be 64, which is nice because then this modulo is taken care of automatically by the overflow and multiplication, and then you don't have to do the modulo, and it's just a shift on a 64. So this is still practical. The only difference is now you actually need the number to be little. You cannot really afford to have 64-bit numbers and the number of bits. You can go to maybe 128. That's a small difference, and you can prove that this one is strongly universal. Not even with a constant. And maybe one difference is that A is not chosen odd anymore, it's just chosen. So you can do this. So there are these examples of strong universal hash functions that are practical, particularly the last one here, have this stronger guarantee. So let's try and see maybe what is one kind of use case of strong universal hashing. So one thing is something like that's I guess called coordinated sampling. I guess there's several ways of motivating this. Let me do one first. So let's say that maybe you are working at TDC or AT&T if you're in the US, one of these companies that are taking care of all the internet traffic. And so what is happening when you're communicating with the server? You have all these IP packages that are being sent across the internet. And so there are all these routers along the way where the messages are being kind of forwarded along different paths until they reach perhaps the destination. So let's say that you would like, if you're the one maintaining this network, maybe you'd like to maintain some statistics about the traffic that is kind of happening online, right? Maybe you would like to be able to see kind of what paths are different packages following and stuff like that. Does that make sense as an application? So maybe you could imagine that you want to, all of these routers if you cannot afford to store all internet traffic, it doesn't make sense. You don't really, you maybe not want to store everything, but you'd maybe like to store a small fraction, say 1% of all the traffic, or 1 in 1,000 of all the internet traffic. What could you do? You could try to sample, of course, the packages that are coming by. So maybe you could imagine that each of these servers is sampling data that's coming by, and it's sampling each package with probability P. Then you could say, okay, how big is the set that I'm going to store here in expectation? Well, let's say that S is the set of all packages that passed through, let's say probably x1 up to xn. Then the expected size, you could define an indicator for every x that counts whether this is sampled or not. Right? So maybe we can say yi is 1 if xi is sampled, 0 otherwise. Then the size of the set that we're storing of this sketch, well, so we can write the total size as y as the sum of these yi's, and then the expected size of the set is, by linearity of expectation, probability that xi is sampled. And into these probabilities p, so this is like p times n. So if I'm sampling every package with probability p, it makes sense that the expected size of the thing I'm storing is p times n. Now, the problem with this is, okay, it's fine for if I want to look at one route and have some representative set of the packages that are passing through. But the issue is, if I would like to maybe track, I would like to be able to trace the path that a package is following across the internet between these different routers. So maybe there's a package that goes like this. How could I make sure that all of these routers will sample the same package? Makes sense that this is a problem, right? Because if all of them samples it with probability p, the chance that this package is sampled on all of those, if let's say there's k of them, they sample independently, the probability they all keep it is p to the k, right? So this becomes very, very small, the chance that you can actually trace it the whole way that it's following across the internet. So what you could do is, you could take a strongly universal hash function. So let's try to do that. So let's take a h is strongly universal. Let's now do the following procedure for determining whether to keep an element that is passing through a router. Basically, here's the procedure for sampling. We just say if hash of x is less than, let's say, p times m, then keep. This is a simple check that I could do. Okay, what's the trick here? Why are we doing this? Well, if I pick such a hash function to begin with, before I start when I set up all my servers, I could distribute the random seed this hash function to all the servers, right? I could just send it to all of them. Make sense? I could just, maybe I could pick my A and my B. I could send it to all these routers. That's very little communication. Now they all share the same hash function. But this means that any two routers are going to keep this data page is kept by one of them, it's kept by all of them. And so you can trace it the whole way through the instance. That's of course great, but we also would like to say that the amount of packages we're keeping is small. Right? So we can try to do this again. Like, look at one of the routers, look at this hash function. How many elements do I expect to keep? I can try to do the same calculations. Everything here is fine, right? I'm just using linearity of expectation. Probability xi is sampled. And this I can still bound, right? Because what is the probability xi is sampled? The probability xi is sampled is equal to, come here, the probability that hash of xi is less than m. Okay, maybe I didn't. Yeah, okay, so one thing to pay attention to with this definition here is, if this is the case that the probability that hash of x equals to q and hash of y is exactly 1 over m squared, it also means that the probability hash of xi is equal to any particular value is 1 over n. Has to be. One can easily show that to get this equality, you need the probability of hash of x equal to q to be 1 over m for all values of q. Just sum up over all the choices of r. So what is this probability? It is the sum from q equals 0 to pm minus 1. Let's say pm is integer. Probability hash of xi is equal to q. How many terms are there in the sum? There's pm terms. The pm terms, all of the probabilities are 1 over m. Pm over m. That's why we chose this p. Okay, so this p is not a prime. Maybe that's a little confusing. Talk about prime. Well, p is a sampling probability. Just to make that clear. This is the sampling probability. The probability that we, maybe I should have called it something. Delta, whatever. Okay, but we're going to keep it with probability p. Oops, there's still a sum over n. So the expected size is p times n. So the expected size is the same as before. Which makes sense. That's where we sample them independently. I can also use the hash function. The expected size of my set is the same. Still p times n. But we haven't really used strong universality yet, right? We only use that one of them is uniform random. The hash value of one element is and in particular, what we're really using is that the probability that you keep your element is p. This is really all we've said here, right? This is all that was needed, is that the probability that you sample it is p. Then you get the right expected size of your sample. But we want to use the strong universality, turns out to be necessary to give a little bit better guarantees, because here's another kind of silly way of sampling where I'm not using a strong universal hash function, but where my expected size is the same. So let's look at this thing here. So then this one is also, I'm also going to distribute, in this case, a hash function to everyone, but not a strong universal one. So this is just to show we need to use strong universality to say a little bit more to make this interesting. So what I could also do is to say, I could say with probability p, every router samples everything. So I could, and otherwise they sample nothing. This procedure still has the same chance of keeping any element, so the expected size of what I'm storing is still p times n. Make sense? The chance that I'm keeping any given xi that is being sampled is exactly. But this seems like a silly way of storing the traffic on the internet, right? I'm basically saying either I store everything with some very small probability or I store nothing. This is pretty useless. Anyways. So we would like to say maybe a little bit more that we can use these estimates for something. Right? Maybe one thing is you can try and say, maybe one thing you could try to say, so you would like to argue that the size of this set that you're sampling is pretty concentrated around p times n. So it's close to p times n, the size of the set percent. That makes sense? So what we would like to do is to try to argue that the size of your sample set is close to p times n with good probability. Well, how can we do this? So here we're gonna make use of a particular inequality, and this one you can always use when you have a strong universal hash function. So it's last time we saw Markov's inequality, we saw the Chernoff bound. This one is sitting in between. It's called Chebyshev's inequality. So this is saying finite variable x yes, with finite variance. So let's say, so then it holds probability that x is further away from its expectation than any t, so this is for all t, is less than the variance of x divided by t. This is called Chebyshev's inequality. So let's try to see if we can use it to say something about how big are these sets that we're going to store, how close are they in size to p times n. Good. So there's some things we can look at this inequality and see what do we need to understand. Let's say x is, this is going to be the size of our set, right? Our sample. It's the one we call y over here. The size of the sampled set. So we need to know its expectation. We already computed that, right? The expectation is p times n. That's good. And then we need to know its variance, right? So that's the other part we need to understand. Right. So what is the variance of a discrete random variable? It is random variable in general. The variance of x, just something to remember here. There's several ways of writing it. I think the most convenient for us right now is the expectation of x squared minus the expectation of x squared. And for us, it will be sufficient to actually use the upper bound. Will it? Maybe let's use the exact range for that. Okay. This is what the variance is. We already know this part here, right? Because this is p times n squared. Now we need to understand expectation of x squared. Let's try and do that. And this is where we're going to use the strong universe. So let's write out what is x squared. And now I guess over there we call them yi's. That's confusing. So maybe let's say what is the expectation of y squared? Well, let's insert what is y squared. Well, y is the sum over I, yi. Like this, right? And I square sum. I get one pair, one term for every pair of elements in the sum, right? So I kind of multiply all terms with each other. So this is now the sum over I, the sum over j, yi, yj. What can I do when I have a sum? Someone whispering linearity of expectation, right? So I can use linearity of expectation here. So I can write it in now as the sum over I, sum over j, expectation of yi, yj. Yi is this indicator that I sampled xi, yj is the indicator that I sampled xj. Now the expectation of a product, when can I simplify the expectation of a product? Do you know any rules for analyzing the expectation of a product? Yeah.
Variables are independent.
Yes. If the variables are independent, then the expectation of the product is the product of the expectations. Okay. What do we have about our random variables? Like these random variables are its xi sample and its xj sample. Basically, its xi sample is a function only of whether xi's hash value is less than p times m. Whether xj sample is a function only of the hash value of xj, whether it's less than p times m. This definition, this pairwise independent, says that the hash values, the pairwise hash values, are independent of one another. And these two are actually independent. These, whether one is sampled, whether the other is sampled. You could also, if you wanted to be really tedious, you could write out, well, this is a product of two variables. Is this sampled and is that sampled? This product is one only if they're both one. You could write out Well, that's the sum over all the possible values of the hash of one of them, the hash of the other of them, where they're both sampled. And then you could sum them all up with this formula here. Give you this. But here we're just going to use, it is a pair of random variables are independent this depends only on the hash of xi, this depends only on the hash of xj. The hash of xi and the hash of xj are pairwise independent. So these two random variables are always also pairwise. Except if I is equal to j. And if I is equal to j, then they're equal. Then I'm saying this xi is sampled, the xi is sampled if and only if xi is sampled. So in that case, I can now write with equality here, this is the sum over I, and now it is yi times yi is just equal to yi. When I have a 0, 1 random variable, which by 0 with 0, 1 with 1, I get 1. So this is basically the probability that xi is sampled. And this is p. And then we have the sum over I, sum over j not equal to I. And now I get, I put it into the product of the expectations. Because they're pairwise independent. Both here are equal to p. This is p. This is p. So this is squared. So I get n times p plus n times n minus 1 terms in the second times p squared. What is the variance now? So this was the expectation of y squared. We have to subtract out p squared, n squared. So the variance becomes here. Variance of this y now is, well, p squared, n squared. It's going to kill all of those terms. And when we subtract them off, n squared is going to kill off all of those terms. And then we still have a minus n times p squared. So it's like n p minus n squared, and that's definitely less than n. So now we have our variance, we have our expectation, and now we can use the Chebyshev's inequality to say something about how likely is it that my set, the size of my set that I'm sampling, is far away from its expectation. Right? In particular, I can choose any t and see what happens. So maybe one choice that could make sense is to say, well, we know the expectation is Pn. Maybe I could try to see what is the chance that it is more than 50% away from that. Make sense? So let's try to plug in p times n half. That's one valid choice. You can try all. It gives you something for all choices. P, right? We could try and look at. Well, basically, we're saying what is the chance that that the size of our set is not in the range from a half Pn to 3/2 Pn. This is basically what we can look at here. What is the probability that it's not in this range? And so we can insert over here, right? So we have our variance is n times p. So we get here probability that x minus expectation of x is the difference here is greater than p n half. It's less than the variance, which is n p over p n half squared. What do we get? So there's an n that kills an n, a p that kills a p, and the 4 that moves up. Oh, p something. So basically this is pretty good, right? It's saying the chance that I'm even 50% away in the size of my set is really small in how many I'm storing, right? This Pn is how many am I storing. So you could imagine if I had a couple of megabytes of memory in these routers, maybe I don't know, I could easily store maybe a million elements, and Pn is a million. Then it's like super unlikely that you'll be storing, I guess, 4/1,000,000. The probability of even be storing more than this within a 50% of the Chebyshev. So here we're using strong universality, where we're basically analyzing this expectation of y squared that we folded into all these pairs of the product of a pair of random variables depending on two hash values, and that's where we could use the pairwise independence to split it out into a product of expectations. Right. So this is where we're using it. Maybe one thing to also, you could ask yourself, like, could we have used universal hashing alone? And actually, there's some things that show that maybe you cannot. Particularly if maybe not this concrete example is not completely clear, but maybe if we go back to this, the multiply shift, the one we had before, right, where we just did AX, and then this mod 2 to the W, and then afterwards did integer division by 2 to the W minus L. And we picked A odd. One thing to notice here, if the way that we're choosing who to sample is by checking whether the hash value is less than something, then we have a problem with some keys are always sampled. If X is 0, that's a particular element. If I'm element number 0, I always get sampled. This is maybe not so the desirable property to have. That some elements are always sampled. There are some other examples, I don't think I'll go through them, where again, these causes issues, that you have some elements that are really different. So really, we're using the strong universal definition here to get this pairwise independence and argue for concentration on how large is the sample that I'm storing. Good. Do I want to give more examples? I think I want to end with just saying, like, a generalization of this that may not use a little bit later in the course, but just to show you what how you can strengthen this requirement or this definition. Maybe also, if you remember from the previous lecture, yeah, question? Second?
Inequality.
Did I not square the t? Yes, I'm missing a square. I squared it when I used it, but I didn't write it. You're absolutely right. Sorry. Good catch. Let's say t squared down here, and I did square it when I plugged it in. But yes, sorry about that. That slipped. So of course, right there, we have to square it in here, or else we wouldn't get the bounds that we're claiming. Good catch. Okay. So then there's a nice generalization of pairwise independence to k-wise independence. So k-wise independence. And it's basically the natural thing. It is that any set of k keys hash independently of one another. And then maybe a formal way of saying it is for all distinct x1 to xk, for all values, say q1 to not necessarily distinct m, probability that for all I hash of xi qi is 1 over n to the k. Okay, so this is kind of like a generalization of the pairwise independence, saying that any set of k keys hash uniformly and independently. We saw last time we were using for the hashing with chaining, we had this property. We showed that if we used the Shannon bound and had a truly random hash function, then we could argue that we could show that with good probability, every single linked list in hashing with chaining had size log n over log n. Remember this from last time? So that required the Shannon bound, which required full independence amongst these hash values through randomness. Strong universality is not enough to get that guarantee. You can show, and we're not going to show it here, but you can show that if I instead use a k-wise independent hash function for k being order log n over log n, you get the same. But this is trickier to analyze, but you can show it with, if I have such a hash function, you get the same. What could such a hash function look like? There's one simple example that I'll show you, and that is basically a generalization of this ax plus b. So pick, let's call them a0 to ak minus 1, uniformly, independently in B. And now you're hashing from, your hash function just goes from P to P. Then you could do the hash of x is equal to, but you evaluate this as a polynomial, the sum from 0, k minus 1, ai times x to the I. This is kind of like a generalization of the previous one. You can show that this hash function here, a degree k minus 1 polynomial, gives k-wise independence to the hash function to choose the coefficients of the polynomial independently and uniformly at random stretch. So that's a way of getting a k-wise independence. And now if you wanted, we didn't give the definition of approximate strong universality and approximate k-wise independence, but in general, if I should say that if you do this and then do another mod m, like we did in the simple case we had for the ax plus b mod p mod m, you do a mod m on top of this thing, you get that approximate version of ky. So you just add a mod m if you want to hash to a smaller range. So, and that actually preserves, it doesn't preserve exactly that it's uniform random. You can imagine that because you're doing mod m, it's uniform random before you do mod m. Now because m doesn't divide p, you have this last bucket of values where you don't see exactly every value of mod m. It's not exactly uniform, but it's close. But it actually doing mod on these values afterwards still preserves the k-wise independence. The hash values are actually k-wise independent. They're just not exactly uniform random. They're close to it. Yeah. But here it suffices, so you can have these kind of slightly high degree polynomials, then you can get the guarantees that we had last time on the length of the longest linked list in hashing with chaining. Good probability it's at most log n over log. But we're not going to do. Yeah, so that is all we had today.